Hello everyone, we are in period 4 and we are doing narration. Everybody's kind of looking at me like, what are you doing? However, what I want to do is I want to read the problem. That's the first slide, and if you're looking at this from home, make sure you have a paper, pencil, calculator. You prove each slide, and more importantly, you try to predict what the next slide might be. So work the problems out. If you're just listening to the video without participating in some way by writing or calculating or whatever the case may be, you're not going to get a lot out of this video. Does everybody understand? Okay, I'm kind of talking to the class, but I'm talking to a computer. But does everybody understand? Okay, it's really important. So this problem is, how much energy does it take to change 2 kilograms of ice at negative 20 degrees Celsius to 2 kilograms of steam at 120 degrees Celsius. Now, I did this with all of my classes, but what I'm going to do is I'm going to put this on the web, and you can follow it along as I do the problem right now. So I'm going to turn the narration off for a minute, and I'll be back in a moment. Okay, I'm making this slide a little longer because I want to encourage the students in my class right now to ask questions, and they'll raise their hand, and then at the end of that slide I'll stop the narration and we'll talk about the question, and then we'll ask the question on the next slide's narration. Now, this is a phase change diagram. You'll see that this is in 5 steps. We're going from negative 20 to positive 120. You see the temperature changes at the bottom. You see the temperature at which the water is at any particular point, negative 20 to 120. You see the plateaus at 0 and 100, heat of fusion, heat of vaporization in terms of joules. So we're going to use this as a template for calculating the needed quantities that are based in the question. Okay, so let's go to the next slide and we'll see what we do. Now, this is the diagram. Another look at it. Now, when I do the problems, everyone, we're going to use water as a model. And why are we using water as a model, Erica? Any idea why we're using water? Why are we using water? As a matter of fact, when we do phase changes, we're just using water. We're not using gold or hydrogen or nitrogen. They have phases. Solid gold, everybody knows what solid gold is. Anybody have gold on? Some form of gold? Okay, we have a gold person back there. Anybody have any bling that has gold in it? That's a fun word to say, isn't it? Bling, okay? So that's a solid. Now I can melt that gold and it would be a liquid, correct? But I'm not familiar with gaseous gold, are you? I'm not. Liquid nitrogen is really cold. But solid nitrogen, I don't know if that could happen. You know, probably could, but the point is that water, everybody has interaction with water every day. And everybody has interaction with ice, water, and steam at least several times a week. Has anybody ever, when was the last time anybody saw ice? In a refrigerator? Has anybody seen ice in the last 48 hours? Okay, they're all raising their hand except for a few people. Has anybody seen steam in the last 48 hours? Okay, everybody's raising their hand. So that's why we're using water, because everybody's very familiar with water and its 3 phases. So study this diagram. The equations for each step are there. Every time we do a calculation, if we're doing a calculation within the solid phase, it's going to be always Q1. When we do a problem and there's a transition between solid and liquid, we're always going to call it Q2. So this is one of your more important diagrams. Now, here are the corrected equations. The equations from the prior slide, Q1, Q2, Q3, Q4, Q5 are all there. See that? And I plugged in. So Q1 is within the solid state, so that's going to be 2 kilograms. All the masses are 2 kilograms. I think you see that. 20 degrees, negative 20 to 0 is 20 degrees. The specific heat capacity of ice is 2,060, and that's in joules per kilogram degree Celsius, so that's 82,400. And then The next one is the mass times the heat of fusion. And notice that's 335,000 joules per kilogram. Some books say 334 joules per kilogram, but just whatever I give you or whatever you see, as long as it's reasonable, you can use that. And then the next one is the liquid. That's 100 degrees because it's going from 0 liquid to 100 liquid, 100 degrees. The next one is heat of vaporization. Look at the heat of vaporization, 2,260,000. That's an enormous value, isn't it? Look, it only takes 4,000 joules to change 1 kilogram of water 1 degree, right? Right? So if you're talking about 100 degrees, which is a lot of heat to 1 kilogram of water, that's like a liter of water. And it takes 837,000. But look at it, 2 million, and it's not even changing a degree. So steam will really burn you. And then the last one, Q5, is 20 degrees, and that's 2,090. So the total is 6,193,400, and that's the answer. So look at that carefully and make sure you can prove that. Okay, here I am with period 6. It's a new class. I was with period 4 with the first 4 narrations. And what we just did was to bring period 6 up to date. We did the problem where how much energy does it take to change 2 kilograms of ice at negative 20 degrees to 2 kilograms of steam at 120 degrees. And we found that it was a 5-step process based on the graph that we introduced in the first few slides. This is a second problem, a little bit more complex, but actually in some ways easier. It says a bowl contains 0.7 kilograms of soup at 95 degrees Celsius. The soup is cooled by putting a 0.4 kilogram ice cube at negative 20 degrees into the soup. What is the final equilibrium temperature of the soup? Now, the ice is going to warm up, so the ice is going to gain heat, and the soup is going to lose heat. The ice is going to melt. It's going to go from negative 20 to 0 degrees solid, and then it will gain heat of fusion, which would be the second step. Then the third step would be it's heating up to around 80-some degrees, and the equilibrium temperature will be actually the temperature of the soup and the ice cube after it melted. So it's not the equilibrium temperature of the soup necessarily, it's the equilibrium temperature of the soup and of the ice cube specifically. Okay, so the next slide, we're going to start doing the calculations based on the graph for Q1 through Q3 and the equations that are on each particular graph. Understand that? It's like a birth defect where you don't have a bubble detector. You're missing your bubble detector. Like I have a problem with filtering myself when speaking. You don't have a bubble detector. Do you understand? He has a crush on you, Morgan.
I don't have a crush on her.
Okay? He does. I know he does. So ignore him, okay? All right. And you can tell him, get out of my sphere. Okay. Zachary. All right, listed on this particular slide are the constants and the information that's given in the problem. Let's take a moment to go over these values. The soup is 0.7 kilograms. That's the mass of the soup. So we're working in kilograms. That's important to know for reasons I'll talk about soon. The ice is 0.04 kilograms. That's 40 grams. That's a significant ice cube. That's a significant ice cube. The initial temperature of the ice is negative 20 degrees. That's also very important. The initial temperature of the soup is 95 degrees. That's almost boiling. That's too hot. You'll burn your tongue. The flesh inside your mouth and around your lips is extremely sensitive to heat. It's not like your skin. It's not like your outer covering. Your outer covering is much more durable and not nearly as sensitive to heat. So we're going to cool it off with an ice cube. The specific heat capacity of ice is 2,060 joules per kilogram degree Celsius. The specific heat capacity of water, what I'm doing is I'm calling liquid water just water. That's what we're calling it. It's 4,187. The heat of fusion for water is 335,000 joules per kilogram. Notice we're working with joules and kilograms and degrees Celsius. Make sure that you have everything in those units, otherwise you'll have to do some conversion so that things cancel out and you wind up with what you need. My class is a little bored, so I want to pick up the pace a little bit. Here we have the equations that we're going to use. I'm actually deriving the equation that we're going to use. You see that the initial equation is the heat lost by the soup plus the heat gained by the ice is going to equal 0. Solving for heat lost, that's going to be heat loss of the soup equals the additive inverse of the heat gained by the ice. So the heat loss side of the equation will be the mass of the soup times the temperature change of the soup and times the specific heat capacity of the water, liquid water, because the soup is mostly water. The heat gain side of the equation is going to be in 3 parts. Q1 is going to be the phase where it's going to be in the ice phase, solid phase, and you're going to multiply by mass change in temperature, which is going to be 20 degrees, and then the specific heat capacity of the ice. Q2 is going to be the mass of the ice times the heat of fusion. Q3 is going to be the mass of the ice, now that's in liquid form, times the temperature change that you don't know what it's going to be because it's going to be TF minus 0, which would be the initial temperature, and then times the specific heat capacity of the liquid. Now, I'm going to say that, so heat gained, if you look at the bottom, the next to the last equation, that's each Q is there, and then I have heat lost equals heat gained on the bottom, and that's going to be the actual equation that we're going to plug into. So now you have your data table on the preceding slide here. You have your equation here. What I'm going to do is on the next slide, I'm going to rewrite the last equation, and we will then plug in and get the answer. Okay, my class is getting a little boring. I'm going too slow, so I'm going to have to speed things up. Okay, Kelly's being very snarky, and Ramian is doing the Kelly interpretation of her snarkiness. Okay, I'm rewriting the equation at the top of this slide. And then underneath that, I'm plugging in the values. 0.7 is the mass of the soup. I'm leaving off the kilograms, degrees Celsius, joules, etc., because it just looks cleaner. Because remember I said to you in the beginning, the kilograms is make sure everything is the same. So we're working with kilograms, degrees Celsius, and joules. As long as everything is in those values, you can drop the signs and then attach them later. So notice that I have the 0.7 times the temperature change, TF minus 95, times the specific heat capacity of water, and then that's going to equal, now notice, it's brackets, it's the additive inverse of the 3 heats. The first heat is the temperature change, TF minus the initial, so it's minus a negative 20. Don't forget the negative sign there, that actually becomes positive. And then, so everything is plugged in there. And now the next slide, what we're going to do is we're going. So that's the physics is done. This slide finishes the physics. Everything is plugged in. Everything is where it should be. The next 2 or 3 slides is simply, solely, and specifically mathematical, where we will reduce things to the simplest mathematical state. Now, here on this one. This, we're going to multiply 0.7 times 4,187, that's 2,931. And then I bring that down, times the quantity TF minus 95. And then 0.04 times a positive 20 times 2,060 is 1648. 0.04 times 335,000 is going to be 13,400. 0.04 times TF, I'm sorry, 0.04 times 4,187 is 168, and then that concludes that second line. Now, I'm going to distribute 2,931 with TF at 95, and I get 2,931 TF minus 278,445 equals the additive inverse. I combine 1648, a negative 1648, and I'm sorry, a positive 1648 and a positive 13,400 to 15,048. 168 times TF is 168 TF, and then the minus 0, it falls off. Now you take the next step on the next slide is going to be the additive inverse of the right-hand side, and then we'll continue with simplifying it. This is simply, solely, and specifically Algebra 1, and just simplifying a rather complex algebraic equation. Now, the next slide, I'm going to bring the last line of this slide to the next top of the next slide, and it's 2,931 TF minus 278,445 equals negative the quantity 15,048 plus 168 TF, and then I'm going to take the additive inverse of that quantity so that I get the last line. I get 2,931 TF minus 278,445 equals negative 15,048 minus 168 TF. Now, notice very clearly here that I want to keep things positive. So I'm going to add 278,445 to the left and the right side, so that'll cancel on the left. So in reality, you're saying a positive 278,445 plus a negative 15,048 is going to be what's left on the right-hand side. I'm going to add 168 to both sides, so it's going to be 2,931 TF plus the 168 TF, and that'll be what's left on the left side, and then I'll divide through, and ultimately I'm going to get the TF. So just keep in mind that the hardest thing about the simplification, algebraic simplification of this, is your signs. You're going through several sign changes. You're taking 0 minus a negative 20 for the first delta t for Q1. So you're also taking the additive inverse of the right-hand side. So just keep in mind, everybody, that what people do wrong in this is they drop a negative sign. And what I will do when I give quizzes on this material, as you know, I don't give partial credit, but what I will do is I will in the answer table, I will break it into parts that you need in order to solve it. So if you make a mistake early on or later in the problem, you'll get credit for what you did up until that point. Understood, Kelly? Morgan is absolutely positively right on task. Morgan's mother, she's a wonderful child. She is absolutely on task. This is on the web, so Mrs. Morgan's mother, she's a wonderful child. Excellent. Well done there, Morgan. And so you can see what we did was I'm going to add 168 TF to both sides. I get 3,099 TF on the left side and 278,445 to the right-hand side. I get 263,397. Divide through by 3,099. I get as a final answer 85 degrees Celsius. My last comment will be that if the answer is between the starting temperature of the ice and the starting temperature of the soup, you're probably correct. Okay? I hope you enjoyed the slides and have a